Hello, and welcome to Fact-Based Living. On this episode, we're going to take a look at Coriolis forces and why you can't oversimplify things. So stay tuned for that. Hello, and welcome to Fact-Based Living. First off, let me apologize for the quality of my voice. I've been fighting the flu for the past few days, and I'm staying home so as not to get my coworkers sick. But I figured I had some time on my hands, and I wanted to make a quick video because I've seen a couple of things on YouTube about the Coriolis Effect and storms, and there seem to be some misconceptions about how it works. And the explanations that some people have given haven't quite been all of the story. So let's just dive right into it. I'm going to pull up a nice white pen. Okay, so the Coriolis effect, we know, tends to make storms in the northern hemisphere go counterclockwise and clockwise in the southern hemisphere. The reason for that is pretty simple. At the equator, you're moving about 1,000 miles per hour in this direction, west to east. But as you go up in latitude in either direction away from the equator, your horizontal, in this case, speed slows down because you're swinging through a smaller radius circle at each one of these, different latitudes. So the net effect of that is the southernmost portion of a storm is traveling a lot faster in that direction than the topmost, northernmost part of a storm. Or in the southern hemisphere, the northern part of the storm is traveling faster west to east than the southernmost part of the storm. And so what this does is it introduces shear onto the storm and causes it to rotate. Since this is going faster at the south than at the north, it's going to rotate counterclockwise. So let's look at what actually happens with the storm, and maybe this will make things a bit clearer. So here's a northern hemisphere hurricane. If you notice, it's swirling in counterclockwise. So why is that? Well, let's look at it. First off, the center of a hurricane is a massive low pressure area. So that means that higher pressure air from around the storm is trying to make its way into that low pressure area to equalize the system out. So it's going from high to low. But because, depending on which direction it's coming in from, it's going to have a different horizontal component to its motion. That's going to affect how it enters the storm and the kind of energies involved. So let's take a look at how that works, starting from the south. So here's our low, and our air is trying to come in this way. But because the air from the south has a higher horizontal component to it and is traveling faster to the right than the air right here where the low pressure storm is, or where the low is. The net effect of that is that this air is going to carry its momentum around, and so it's going to bend off in this direction as it travels northward. So let's look now at air coming in from the east. It's going to come in, but it doesn't really have a different horizontal component to it than the storm. So it's coming in this way. It doesn't have a little arrow like this pulling it to the side because it's already at the same latitude as the eye of the storm. But what is going to happen is it's going to butt up against this air that came in from the south. And that air from the south is going to transfer some of its momentum to this air coming in from the east. So this air from the east is going to come in, it's going to hit the air from the south, and it's going to get driven to the north. You can already see the pattern that's developing here. Now, air that's coming in from the north, it's coming in with an even smaller left to right component than the eye of the storm does. So essentially, the eye is moving this way as this air comes in. And so the effect that has on the air coming in is that the eye is drifting to the right as the air comes in, and its momentum is going to make it continue off to the left here. And so it's going to swing around the backside of the eye like this. And the same thing happens with air coming in from the west, is it's going to come in, it's going to impact this air coming in from the north, and it's going to get bowed around this way. And that's going to have the net effect of causing all of this to rotate around counterclockwise. So that all should be fairly, straightforward and common sense. But the thing that seems to be confusing everybody is what happens if instead of a low pressure cell, you have a high pressure cell. So let's take a look at that. So let's put our high pressure cell in here. Now what happens with a high pressure cell is you have air coming in from the upper atmosphere that is getting rapidly cooled. And so that cooler air becomes more dense and begins to sink. And so it's moving downwards like this. And then as it comes down to ground level, it's going outward in every direction. And that creates a high pressure cell right where the air is sinking down. It's basically the exact opposite of how a hurricane works. So let's look at what happens to the air leaving a high pressure cell at the exact same latitude as our hurricane in the previous example. So let's start again with the south. Now, the air is going to try to go straight out south like this, right? But all of the air down here is trying to move from left to right, west to east, at a much higher velocity than what it was, say, up here, where it's a smaller velocity. So the net impact of that is it's going to cause this air to appear to drift. I'm going to go back to yellow so you can see. It's going to cause the appearance of the air to drift this way as it exits. The same thing happens with air trying to leave out and go to the west. It's trying to go this way. And of course, the storm's trying to move this way. And so it's just going to kind of go along on its happy way this way. Now, what happens to air going to the north? Well, it's going here where there is a smaller moment put on it from west to east than what it's leaving with. And so its momentum is going to carry it the direction it was already going, which is eastward. And so it's going to bend this way. And then air coming out this way is going to bend this way. So what ends up happening is the east and the west currents get driven by the air coming out at the south and the north, and until the entire system swings around clockwise. In this case, it actually wouldn't be spiraling in. What's happening is at your high pressure point, everything is coming out this way. It's all bending in a clockwise manner as all these different air currents interface with each other and shove themselves around. And that seems to be where the confusion came with this picture. In the video, it showed you have several storms here, and some of them are rotating clockwise the way you would expect them to, or counterclockwise, I mean, the way you would expect them to. Like, I don't remember which one is which, but we'll say this is one that was going counterclockwise like it's supposed to. But then over here, you had this weird system that was going clockwise. And I think there's another one, maybe it was this one, that was going clockwise. And so the argument was, well, that debunks the whole, Coriolis effect. Well, except for the fact that this here was a low pressure system, and these ones over here were clearly high pressure systems, whichever ones were rotating clockwise. Because a high pressure system is always going to have the opposite rotational effect as a low pressure system, depending on what hemisphere it's in. So in the northern hemisphere, a high pressure system will rotate clockwise, and in the southern hemisphere, a high pressure system will rotate counterclockwise, exactly backwards of its low pressure, mates. And you can see this when you look at the weather charts. In fact, one of the good places to get really nasty choppy air and bad storms is the interface in between a high pressure system and a low pressure system, because you've got air going in opposite directions of each other, and you end up with this massive shear pattern right in the middle of them. So that's the takeaway from this, is that low pressure systems rotate one way, high pressure systems rotate the other way. And that's why when you look at a polar storm map, or really any storm map, you'll be able to see that some of the storms rotate one way and some of the storms rotate the other way. And both of them are powered by the Coriolis effect. The rotation is, at least. They just have opposite rotations because of the opposite flows of air. Low pressure system, the air is coming in. High pressure system, the air is coming out. So I hope that made sense to you. I've got some new animation software that I'm going to hopefully be debuting here fairly soon, and I can start making some better videos that look less like a whiteboard. And I got myself a nice boom mic and everything set up, so hopefully there will be a lot less desktop noise and stuff like that when I'm recording, and that should drastically improve my audio quality. But as always, I really could use the constructive criticism on my videos. Tell me what I'm doing right. Tell me what I'm doing wrong. Go ahead and leave me a comment down below. If you like this, found it informative, please share it with your friends, family, anybody you thinks could use it. And give me a like and subscribe below. All right, this has been Fact-Based Living. I'll talk to you soon.